Actually, the modeling of fractures in geological materials. So in this talk, I'd like to share some interesting modeling studies I've done with my colleagues in the past few years to address the fracture complexities in geological materials. So let's just get started with the very basic question. Why is it important to study the geological fractures? And the answer is clear because they're everywhere and important to our life. For example, when you are out for hiking, you may see the joints of fractures in this rock slope, and those fractures become large enough, you might be worried about the slope stability. And also the earthquake, one of the most concerning hazard in the world, are mostly triggered by this dynamic motion of the geological force, and this geological force can also be treated as the fractures of discontinuities as well in the Earth's crust. And besides this natural world, the geological fractures nowadays also play a more and more important role in the engineered system. For example, as this figure show, it shows the example of the enhanced geothermal system where the high pressure fluid is injected to the hot dry rock to artificially create the fractures here so that the reservoir has sufficient hydraulic conductivity for fluid circulation and heat production. But the challenge is studying geological fracture is never an easy work because they involve so many complexities. And first, for example, they commonly show this complex structural or geometric patterns, like this mixed mode cracking in rocks under compression, where we can see this curved tensile wing crack and also the coalescence between the shear cracks and the tensile cracks here. And also this core of the geological force can also be very complex, like the figure shown here, where you can see many structural elements such as the damage zone that is filled with these micro cracks, and also the fractured or localized fault zone where the fault slip concentrates. And apart from these complexities in the fracture pattern, the mechanical behavior of the fractures can also be very complex in the geological materials. For example, different from the purely brittle fracture, where we usually expect the stress singularity at the crack tip, the geological fracture, as you can see here in this right figure, is usually characterized by this fracture processing zone, where the stress reduces from a finite peak value to a residual value. So what are the causes of these complexities? There can be many answers, but I believe most of them can fall into these three aspects, which are the material, structural or geometric, and also the in situ conditions. So for the material aspect, it can include the material heterogeneity across the different scales and the intrinsic material nonlinearity, such as the plasticity of the rock. For the structural or geometric aspect, for example, the geological materials such as the rocks can have pre-existing joints or defects that can sometimes determine the final cracking pattern. Also, the geological fractures are never smooth, but contain a certain level of the roughness, which can lead to sophisticated friction law and volume change when the fracture moves. And as for the in situ condition, the effect of the in situ stress on the rock fracture and failure pattern has been an important topic for at least 10 years. And as the development of the subsurface system becomes more and more popular nowadays, the characterization of the in situ pressure and temperature also becomes crucial to understand the fracturing behavior in some super hot and super deep condition. So to better understand and predict the fracture growth and its behavior in geological materials, the numerical models play a very important role here and can provide us with some benefits that experiments and the field test alone cannot give. For example, we can better control the initial and the boundary conditions in the numerical simulation than the laboratory test. And also it gives us the more flexibility to change a parameter such as the pressure and temperature and see their impacts on the resulting geological fractures. And most importantly, the geological materials are usually not transparent, so it's very hard to visualize any fractures or cracks inside the sample. And sometimes we have to rely on some like CT scanning or X-ray acoustic emission to visualize them, but the numerical models make it more convenient to observe what's happening inside the sample. And because of this high demand of the numerical modeling to study the geological fractures, a wide range of the tools have been developed. Like here, I've divided them into three categories. The continuum-based method, which includes a classic boundary element and finite element method, as well as some more advanced method like the embedded or enriched finite element method and extended finite element method. And the second category is the particle-based method, like the discrete element method. The last category is the kind of the hybrid technique that takes advantage of both continuum and particle-based method, and some representative example includes SPH, paradynamics, as well as the material point method, which also becomes very popular nowadays. But even with the advancement of the computational modeling and the increasing computing power, the numerical modeling of the geological fractures still remain pretty challenged. And here I've listed some of the main challenges or questions we should address. For example, is the method computationally efficient and robust to deal with those fracture complexities? And is the method physics-based and reliable to model the fractures? Is the method able to give unique solution regardless of the numerical parameters we set? And last but not least, is the method simple enough to implement? So with all of those questions in mind, let me move to this slide to introduce the potential candidate for modeling the geological fractures, which is the phase field method, which I have been working on like for last 5 years since my PhD. And let me just briefly describe this phase field method first. So in the past, when we want to model the fractures in a continuum medium, we commonly consider the fracture as a sharp interface, as you can see here, with zero thickness. And if we want to draw the spatial profile across this fracture, it's like a delta function, as you can see in this right figure. But the phase field method essentially approximates this sharp interface representation by a diffusely distributed damage variable, which we denote by D here. And you can see the spatial profile also transform into a shape that has a finite width, which is governed by this length parameter L here. And the value of this phase field variable ranges from 0 to 1, with 0 means the material is intact, while 1 means the material is fully fractured or damaged. So to model the fracture growth with the phase field method, we basically need to solve this partial differential equation to update the phase field variable. And in this equation, the first term generally represents the release of the stored energy, and the second term means the energy dissipation associated with the fracture growth. So if you're familiar with the fracture mechanics, you can quickly realize that actually this phase field equation is consistent with the classic Griffith theory, which is the core of the fracture mechanics principle. And it means the phase field method itself is physics-based. And also to solve this partial differential equation, we can just use the standard finite element method or finite volume without any additional algorithms to track the fracture geometry. So it will make the implementation much easier than many other advanced methods. And to better demonstrate this advantage, here I'm showing you this animation, and you can see with the standard finite element grid, we can capture this curved fracture growth from the initial crack tip. And another notable feature is the phase field method is essentially a non-local method, just like the non-local damage model. And it has this diffuse region that regularizes the singularity. Therefore, the phase field solution has a good mesh convergence and different from some of other methods that may suffer the mesh sensitivity issues, such as some local damage method or the stress glut method that is commonly used for the fault mechanics modeling a few decades ago. So because of all these features, the phase field method performs pretty well in modeling the fractures, especially when the the fracture geometries are very complex, like what's shown in this left figure. And also it can easily handle the fracture growth in heterogeneous materials, and the simulation can be simply extended to 3D. So with all this, the phase field method becomes more and more popular nowadays, and we see increasing applications to model the geological fractures in the past decades. But the problem is, when applying to the geological fracture modeling, the phase field still has a number of limitations. For example, the original phase field formulation is completely energy-based and designed for purely brittle fracture, but for the geological materials, especially the rocks and rock-like materials, they're characterized by this quasi-brittleness, which means the fracture nucleation is mostly governed by the material strength. And also, most of the phase field modeling focus on the mode 1 fracture under the tensile loading, but geological materials are mostly under the compression, and therefore the different fracture modes, including mode 1 and mode 2, and we can even observe the mixed mode pattern in the rocks if it's under some compression. And another important part that is missing in many previous phase field studies is the model didn't account for the friction and its associated energy loss. But for geological fractures, there is substantial amount of the friction when it's under shearing. So to fill these research gaps, I've been working on extending the phase field method for many specific purposes. And here I'd like to introduce 3 of them that individually focuses on the frictional shear fracture, the mixed mode cracking in rocks, and the near well hydraulic fracture nucleation and propagation. And I will first talk about this modeling of the frictional shear fracture. And let's first record this original phase field formulation. And here, this first term only accounts for the release of the elastic string energy. So in order to account for the effects of the friction on the shear fracture propagation, we introduced an additional term in the equation, and this psi f here basically represents the energy loss due to the friction during the shear fracture propagation. And through some derivation, we finally get the expression of this H plus term, which we call the crack driving force term in the phase field equation. And at the same time, we also consider incorporating the friction into the mechanical response by splitting the stress tensor into 2 parts. The second part, which I would like to highlight here, denotes the interface stress, which is basically to account for the friction stress on the interface. And its calculation can be done by solving these 2 following equations I've listed here. So we have done some verification for this model with a classic fractional mechanics problem and further apply this method to a slope stability problem, as you can see on the screen. So the problem setup is original from this paper, where they used the embedded finite method to model the growth of the slip surface when subject to this compression load on the rigid foundation. So here it shows the growth of the slip surface modeled by the phase field method and compared to the solution obtained in Rigoro and Boha, you can see the location and the shape of the slip surface actually match pretty well between these 2 methods. And also, I was quite surprised and very honored to see this simulation work has inspired many following modeling studies, especially on the non-local damage method and the phase field method, where the researchers are comparing my phase field solutions to their modeling results as well in their papers. And of course, it's not the end of this work. We thought this model can also be pretty variable for modeling some very important shear fracture problems like the slip and growth of faults. So we further extend the model by incorporating the rate and state dependent friction for geological faults. And also we make use of this quasi-dynamic approach to capture the fault rupture for computationally efficiency. To verify this model for the geological fault, we have designed this 2D plane strain problem where the horizontal fault has an initial normal stress and the shear stress, and it's in the steady state. And to initiate the fault rupture, we reduce the fault friction inside a small region at the middle of the fault, and the fault rupture will propagate outwards with time. So here I show you the phase field results and the solution from the well-verified method called the finite element spectral boundary integral method, or FEBI in short, for the evolution of both slip rates and also the shear stresses at 3 different observation locations. And you can see the phase field method has the reasonable match with this FEBI solution. And as the time step size becomes smaller, the phase field result actually becomes closer to the reference result, which is something that we expect. And after the verification for modeling this fault rupture, we also want to take the advantage of the phase field to model the growth of the fault slip surfaces. So we designed this example under a continuous shearing. And to facilitate the growth of the slip surface, we assign a weak zone with lower cohesion at the center of the domain. And as the shear increases, you can see this conjugate radial shear bands start to nucleate at the weak zone first. And then this R1 shear bands becomes more dominant. And at the end of the simulation, we can see an array of the slip surfaces, which forms this in echelon structure that is commonly seen in the strike slip fault system. We also compare the pattern of the resulting slip surfaces with that observed in the experiment, and you can see quite good qualitative agreement with the simulation they obtained in this paper. So for more details, you're welcome to check out our recent manuscript on this phase field modeling of the quasi-dynamic rupture, nucleation, and propagation of the in-plane faults, which is also currently available on arXiv. So, and another interesting topic I would like to talk today is this mixed mode cracking patterns in the rocks. And as we are from this rock mechanics community, we know that this mixed mode 1 and 2 cracking pattern commonly take place in rocks under the compression. And it's important to note that these 2 fracture modes actually have a quite distinctive features. For example, the mode 1 tensile crack is open and has no friction, but for the mode 2 shear crack, they have the substantial amount of friction. And also, the critical fracture energy for the shear crack is much higher than the mode 1 tensile crack, according to the experimental measurement. So because they're quite different intrinsically, we propose this double phase field idea that uses 2 separate phase field variables to model the mode 1 and mode 2 fractures individually. And you can see this demonstration in this figure. So for each phase field, we use the model that is well suited for the corresponding cracking mode. For example, we use this cohesive fracture phase field model for the mode 1 crack and my previous frictional shear fracture model for those mode 2 cracks. And to validate this model and demonstrate the features of this double phase field model, we refer to a classic problem set up in this paper by Bobet and Einstein, where a rectangular specimen with the 2 parallel pre-existing floors is under the uniaxial compression. And in both experiment and simulation, the different configurations of these pre-existing floors have been tested by changing this inclination angle alpha and also the stepping between these 2 parallel floors, which we denote by W here. And here I'm showing you 2 cases of the simulation. Both have the same inclination angle, which is the 45 degree, but the stepping is different. So for the first case, the stepping is equal to the half floor size. And we can see the initiation and the propagation of the tensile wing cracks first from the floor tips. And the shear cracks in blue color also extend from the floor tip. And finally, we see a secondary tensile crack here at the middle that correlates with the two shear cracks. And for the second case, where we have a larger stepping, we still see the growth of the both tensile wing cracks and the shear cracks from the floor tip, but the coalescence happens as the wing crack directly connects with the shear crack from the floor tip. And we don't see any secondary tensile crack in this case. And for both cases, they matched with the experimental observation. And through this example, I want to highlight another advantage of this double phase field method, which is that you can see the model can help distinguish between the cracking modes. And this can be very useful to understand the cracking mechanism when it's hard to interpret the cracking mode experiment or field test. So with this double phase field model, we further apply it to a 3D simulation where the rock sample has the internal embedded floors, and we want to investigate the cracking behavior under a true traction compression state. And this kind of task can be very challenging to do in the laboratory because it's very hard to visualize a fracture in the interior of the rock. And that's why we want to leverage the numerical modeling for this study. And so here I'm showing you some representative results we obtained. And for this particular results I'm showing you, they suggest that orientation of this intermediate principal stress has the major effects on the 3D cracking pattern from the pre-existing floors. And also, we study the effects of the stress magnitude, particularly on this intermediate principal stress. And we observe that the specific effects depends on the stress orientation. For example, when the sigma 3 is parallel to the floor, we see the peak stress increases with the sigma 2 magnitude, but the trend reverses for the case when the sigma 1 is parallel to the floor. And if we plot an average peak stress across these three stress orientations, we can see this average trend, as shown in this dashed curve, first increases and then decreases with the increasing sigma 2 magnitude. And it's a very interesting observation as this average trend is exactly something that was observed in the experiment, where the peak stress of the pseudo intact rock under true traction compression also increases and then decreases as the intermediate principal stress increases in magnitude. And this finding from our numerical study strongly supports the conclusion of the old paper by Weibels and Cook, where they claim that this variation of the rock strength with the sigma 2 magnitude might be attributed to the cracking from the randomly oriented floors in the rock sample. And for more details of our numerical study, you can refer to our paper published in the Rock Mechanics and Rock Engineering last year. So while the first two models are mostly focused on the general natural fractures, this last model will be specifically about the hydraulic fracturing, which gave us many important functions to the developments of the subsurface systems. For example, the permeability enhancement for the geothermal system, and also some small size hydraulic fracturing tests can be used to estimate the in situ stress as well. One of the standing challenge for the hydraulic fracturing is this near wellbore region. The fracture pattern can be way more complex due to a number of factors like the in situ stress, rock heterogeneity, temperature change due to the injection through the well, and as well as the wellbore setting, like the wellbore deviation. And because of all this, the phase field can be a good tool to address this near well fracture complexity. The problem is the original phase field model and the most popular one that is used in hydraulic fracturing simulation is derived in a solely energy-based way. But for the near-well hydraulic fracture modeling, it's important to accurately capture the nucleation of the fracture, which is actually determined by the rock strength. So motivated by this, we've devised a new formulation, as shown here, by adding an additional term, which we denote by CE here. It actually represents some like external driving force term in this phase field equation to account for the proper rock strength criterion, such as the Druck-Plagger strength criterion for the rocks. So that by doing this, the model can properly capture the near-well fracture nucleation at the correct stress state, and also it can correctly capture the propagation at the same time. And to better demonstrate the advantage of this model, here we are comparing the solution from the original model without this CE term and our new model for a 2D wellbore problem under a different principal stress in each direction. And because this minimum horizontal stress is in the y direction, we expect the hydraulic fracture initiates at the most left and the right points on the wellbore surface. And the fracture should propagate horizontally. That is normal to this sigma small h. You can see the new model can predict the fracture initiation and propagation direction as we expect, but the original model cannot. And for the details of the model and its verification, you can also check our paper published in 2023. And if you are interested at the model is also available in GEOS, which is an open sourced multiphysics simulator that is developed by the LLNL, Total Energies, and Chevron and Stanford University. And you can scan this QR code for more details of this software as well. I will pause here if you are interested and want to scan the QR code for a second. Okay, so and then let's move to the next slide. So with this phase field model, we are using it together with the laboratory hydraulic fracturing test under the true traction compression to study the near well hydraulic fracture pattern and its implication for the in situ stress measurement. So in this slide, you can see the problem setup and a snapshot of the traction loading facility from Professor Andy Bunker's group in the Pittsburgh University. The sample is the 6-inch granite cube, and we have a cylindrical wellbore at the center. The wellbore can be either horizontal or vertical and can also be inclined as well. And one thing to note that is we only pressurize this middle shaded area along the wellbore to make sure the fracture initiates here. And in order to achieve that in the experiment, our colleague in the Pittsburgh University has designed this special injection tube, which has the two O-rings on the ends of the pressurized zone. And if you have like further questions about this experiment, Yingxin is the person who is doing the experiment, so you better ask him. And we have done a lot of parameter studies, and in this slide, I'm showing you one of the studies that we have done. So, which is on the different wellbore inclination case. So you can see, for example, here, the phase field can capture the change of the near well fracture pattern pretty well when we have the different wellbore inclinations. And you can see in some cases, we can match the fracturing pattern observed from the experiment, which shows some curved S-shaped fracture along the wellbore direction. And also apart from this experimental scale simulation, we also applied the model to simulate some hydraulic fracturing tests in the field. For example, here, I'm modeling a mini frac test that has been conducted on the production well in the Utah Forge site. And for a more realistic simulation, I've generated the heterogeneous field for rock properties based on the available well log data. This is still a work in progress, and I'm now doing some parameter studies, for example, changing the effective in situ stress to see the impact on the resulting fracturing pattern, and also comparing them with the post-test image log from the Forge site. So now I'm wrapping up this numerical study, especially that work on the left, on the laboratory scale hydraulic fracturing test. And hopefully we will publish something soon. So now let's get back to these questions I brought up earlier and check if the phase field is a good candidate to model the geological fractures. First, the computational efficiency and robustness. Of course, the phase field gives us the robust way to handle the complex fracture geometries like the branching, intersection, and kinking. And is the phase field method physics-based? Yes, it is derived from the fracture mechanics principle. Is the phase field solution sensitive to any numerical parameter? For this aspect, I didn't show example here, but as I said, the phase field is like other non-local methods that have this mesh objectivity feature. And you can also check my papers. We have done a lot of this kind of mesh convergence studies for the phase field models we have developed. And lastly, is the phase field method easy to implement? Yes, it can be directly handled by the standard finite element, finite volume, and the finite difference. So compared to many advanced methods nowadays, its implementation is like way more easier. So at this point, I think we are confident to say that the phase field is a promising method to model the geological fractures. But of course, I say the phase field is still very young in this field, and there is much space for improvements, especially on the computational cost and the displacement jump calculation across the fracture. So I also like to, at this moment, I also see many researchers, including myself, are taking efforts to make the model more comprehensive and also more robust. So I also like to take this opportunity to let more people in the rock mechanics field be aware of this tool and hopefully can have more applications in the geomechanics community in the future. And before finishing my presentation, I'd like to give a special thanks to all my co-authors for the work I have presented here, both in Hong Kong and also my work in Livermore. And also I like to acknowledge the funding support for supporting my work throughout these years. And so that's the end of my presentation. And thanks for listening. And I'm happy to take any question you have.
Thank you so much, Frank. It's an excellent presentation. So any questions from the audience, you can either speak here or type in the chat.
I have a question. Hi, Frank.
Hey, Alex.
Yeah, thank you for the talk. It was very interesting. It's not my field of, it's not from my background, but from a little bit that I understood. Could you speak to how you treat the mesh at the fracture region where the fracture initiates? Because from what I understood, the method looks like an immersed boundary method where you immerse the boundary and then represent it with like the diffuse function. But then you show the like a video where a slab laying on top of like a hail was actually cracking and breaking part of the material. So there I saw actually potentially like mesh, not even motion, but like mesh distortion, mesh cutting, and like certain mesh operations that it might involve. So could you speak to that?
Oh, yeah. Maybe I didn't explain too well, but let me see. From this animation here, well, actually, to answer your question is the phase field master didn't have any like specific treatment for the mesh. We can just use the standard finite element or finite volume mesh or the standard mesh to model the phase field. And even using the Cartesian grid is okay, as long as we have the sufficient resolution within this diffuse region. Yeah, so that's why as I mentioned, that we can just use the standard finite element or finite volume discretization, they can be sufficient to model the phase field. So
how
didn't need any special treatment on the mesh.
So how did you treat then the problem with the slab breaking part of the material, like when it's sliding downward? Because there you show no.
I bet you mean this
Yeah,
example?
this one. Yeah.
Yeah.
Where
So,
basically you actually show the piece of the material is breaking apart.
this is just kind of the post-processing in the visualization. I don't know if I can just play it here. So basically, I'm kind of like showing this deformations by like making the grid that is like deformed based on the displacement I have solved.
Mhm.
And
So-
actually, I believe I have exaggerated, I have like exaggerated deformations by a certain magnitude so that you can see the change more clearly. But it doesn't mean that we have like such large deformation for this simulation. I just want to let you have a clear look of how this slip surface generates and how this upper soil mass or the rock mass can slide along the slip surface. Yeah, so it didn't mean that I changed the mesh. I actually didn't change the mesh.
I see. So the mesh is intact, and basically you don't account for like change of angle. For example, if now the slab is pushing the material at a different angle and not necessarily like perpendicular as it used to be on the top, right? So basically,
Right.
Okay.
That's also one of the most, I would say, standout advantage of the phase field. So you don't need any special treatment on the mesh.
Do you use like some higher order numerics around the crack to reconstruct the gradients across it? Or you use the same methods that GEOS uses, like a 2-point flux approximation?
So, well, I would say all the simulations I have shown here, I just use the linear quadrilateral elements. But of course, there are also people using the higher order elements to for this phase field modeling, but it doesn't mean that it's the requirement.
Okay, thank you very much.
Frank, can you hear me?
Sure.
Oh, sorry. This is Oleg.
Hey, Oleg.
Yeah, I had a question. So if you have a fracture developing, is it just strength degradation, like material loses strength along a certain surface, or it's also elastic property change? So how do you account for, like if you have open fracture, it will affect elastic properties in that area, right?
Yeah.
So like if you send you can even detect fractures using seismic methods because wave field bounce reflect from the fracture. But it seems to me like phase field only captures loss of strength along the surface, not change in elastic properties. Is it a right statement?
I think it depends on the different understanding of the phase field. Of course, I've been working with several people in the computational seismology as well. And I think some people in that field, what they understand about the phase field is, yes, it does change the elastic stiffness. So that's why they are also showing this interest to use the phase field for example, for some earthquake modeling or for the fault growth and fault mechanics problem, because it's gonna be more, I would say, better than the plasticity method, because the plasticity, it doesn't essentially change the elastic properties. But the phase field, it depends on your understanding. It actually adds this degradation on the elastic stiffness. So I would say, yes, you can understand in this way.
Yeah, so basically, if you introduce, let's say, planar fracture using phase field method, then it's like non-compliant fracture basically. So it does not affect normal compliance. So if you measure, if you send the normal to the fracture, if you send the elastic wave, it will go through, right? It will not bounce back.
I think it depends on how you like modify the elastic stiffness tensor. So, I mean, for the original phase field model, it actually degrades all the components for the elastic stiffness tensor. But for some of the phase field models, including myself, I have some, for example, the shear fracture models, I only degrade some parts of the elastic stiffness tensors to kind of retain this normal compliance, like as you said. But it's possible that we can design the special treatment on this elastic stiffness tensor just to fulfill our expectation.
Okay, thank you.
Okay, any other questions? No? Okay, if we don't have another further questions, or if you feel hesitant to ask now, I believe Frank will be more than happy to connect with you offline for further discussion. So I think we can wrap up here today, and thank you all for attending. And we're looking forward to seeing you next time. Bye.
Thanks.
Thank you.
Bye.
Thank you. Thanks, Frank.
Thank you.